All right, welcome. Today we are jumping headfirst into one of the most powerful and, let's be honest, sometimes confusing features of the Go programming language, its concurrency model. We're going to build a solid mental model starting from the very basics, the why, all the way up to the architectural patterns that make Go just so incredibly effective. Let's get right into it. You see, for the longest time, we developers got a free lunch. We could write our code, just simple one-step-at-a-time code, and next year's computer would just run it faster. No extra work for us. It was a golden era. But then, that free lunch was over.
And this timeline shows you exactly why. Around 2005, chip makers hit a wall, a literal wall of physics. Pushing clock speeds higher meant generating more heat, and we simply couldn't cool the chips down fast enough. So the industry pivoted. Instead of making one core faster, they started putting more cores onto a single chip. And just like that, the multi-core era was born, and it changed the rules for writing software.
So here's our roadmap for this explainer. We'll start by digging into that multi-core revolution. Then we'll uncover Go's really unique philosophy. After that, we'll get our hands dirty with its toolkit, Goroutines, channels, the whole shebang. We'll pull it all together with a practical pattern, and then we'll level up and start thinking like a true system architect.
Which brings us to our first stop, the multi-core revolution. Look, this isn't just some hardware trend. This is the fundamental problem that Go was created to solve. Our programs had to learn how to walk and chew gum at the same time.
Now, before we go any farther, we have to get this one distinction crystal clear. It comes from Go's co-creator, Rob Pike, and it's this: concurrency is not parallelism. Think of it like this. Concurrency is about the structure. It's about designing your program to deal with a lot of things at once. Parallelism is about execution, actually doing many things at the exact same time. They're related for sure, but they are not the same thing.
The best analogy I've ever heard for this is a bicycle. When you're riding, your legs are working concurrently, right? One is pushing down while the other is resetting. The design is concurrent, but they're not parallel. They can't both push with full force at the same instant. Now imagine a tandem bike with two riders. That system is both concurrently designed and it's executing in parallel. You've got four legs all working together to provide power.
So, if concurrency is about the design, which design did Go's creators choose? Well, that brings us to its core philosophy, a model called Communicating Sequential Processes, or CSP. And this decision, this choice, is what really makes Go feel so different from other languages.
And what's so cool here is this comparison. In the actor model, which you'd see in languages like Erlang, every little concurrent worker, an actor, has an identity, like a mailbox address. You send the message to a specific actor. But in Go's CSP model, the workers, our Goroutines, are anonymous. You don't send a message to a Goroutine. You put a message on a channel. The channel is the first-class citizen, not the worker. It's a huge mindset shift.
Okay, so let's check out the actual tools Go gives us to build on this philosophy. We're going to meet the fundamental building blocks: Goroutines, the classic mutex, and my personal favorite, Go's secret weapon, the race detector.
First up, the star of the show, the Goroutine. It's really just a function that's running at the same time as other functions. But the magic here is that it's unbelievably lightweight because it's managed by the Go runtime, not by the operating system. And you create one with a single keyword, Go. That's it. And this table, wow, this really tells the whole story. A typical OS thread grabs a megabyte, maybe more, of memory right from the start. A Goroutine? It starts with a tiny 2 kilobytes and only grows if it needs to. The practical result is a game changer. You might be able to spin up a few thousand threads, but you can easily have millions of Goroutines. This completely changes the way you can architect your applications.
But, as they say, with great power comes a really sneaky, silent villain, the race condition. Now look at this code. It seems totally harmless, right? We have a counter, and we're just telling a bunch of Goroutines to increment it. I mean, what could possibly go wrong? The answer is everything. Because that simple little counter plus plus, it's a lie. It's not one operation.
Here's the crucial part. That one line of code is actually 3 distinct steps behind the scenes. So, imagine Goroutine A reads the value, let's say it's 0. But before it can write the new value 1 back, Goroutine B swoops in and also reads the value, which is still 0. They both write back 1. You had 2 operations, but the counter only went up by 1. An increment was lost forever.
This is the stuff of nightmares for programmers, a bug that corrupts your data silently and only shows up under pressure. But Go gives you a superpower to fight back. It's a simple little flag you can add to your test command, -race. When you run your tests with this flag, the Go toolchain actually watches your code for these exact kinds of unsafe memory situations.
And this is the hero moment. Instead of finding corrupted data months later in production, you get this, a big, loud, impossible-to-ignore warning right in your test output. The race detector makes the invisible enemy visible. It is, without a doubt, one of Go's killer features.
So how do we fix this race condition? Well, the classic solution is a mutex, which is short for mutual exclusion. You can think of it like a key to a room. Before a Go routine wants to touch that shared counter, it has to grab the key by calling lock. When it's done, it puts the key back by calling unlock. This guarantees only one Go routine can be in that critical piece of code at a time. Problem solved.
Now, mutexes work. They're a totally valid tool, but Go offers a more elegant, a more idiomatic way to handle these situations. And that brings us to the heart and soul of Go concurrency, channels. And it all comes down to this powerful mantra from Rob Pike: do not communicate by sharing memory. Instead, share memory by communicating. So what on earth does that mean? It means instead of having a bunch of Go routines all trying to access the same piece of memory and using locks to coordinate, what if we just pass the data from one Go routine to the next? The act of sending the data becomes the synchronization point itself.
And channels are how we do it. There are two main flavors. An unbuffered channel is like a direct, synchronous handshake. The sender and receiver have to meet at the same time for the exchange to happen. A buffered channel, though, is more like a little mailbox. The sender can drop off a few messages and walk away, which decouples the sender from the receiver.
And if channels are all the different instruments in our orchestra, the select statement is the conductor. It allows a single Go routine to listen on multiple channels at once. It just waits, and the moment a message arrives on any of those channels, it springs into action and runs the code for that case. This is how you build incredibly responsive, event-driven systems in Go. Okay, so we've looked at the pieces: Go routines, race conditions, mutexes, channels, select. Now let's put it all together and see how these simple primitives can be combined to build a really sophisticated production-grade pattern.
This is a pattern called a concurrent singleton, and it is a brilliant example of using channels instead of mutexes. Here's the idea. One and only one Go routine ever has permission to touch this shared data. We'll call it the owner. All the other Go routines that need to interact with that data send messages to the owner over channels. The owner just sits in a loop, processing one message at a time from its inbox. There's no race condition possible. By design, access is serialized through the channel. No locks needed.
You know, learning the syntax is the easy part. Using it effectively to build robust, resilient systems, that requires a shift in how you think. So let's level up from the code itself to the high-level mindset of a system designer. And this right here, this is incredibly valuable. It's a failure mode inventory. For every one of these concurrent tools we've talked about, you have to know how it can break. A Go routine can leak if it's stuck waiting on a channel forever. You fix that with context cancellation. Mutexes can deadlock if you lock them in the wrong order. This kind of proactive thinking, knowing the failure modes and their mitigations, is what separates good engineers from great ones. And that brings us to the end. I want to leave you with a question, a challenge, to take back to your own work. Now that you know what to look for, that silent villain of operations getting interleaved, of state being accessed without protection, what hidden race condition is just waiting to be discovered in your system?